Hello everyone, welcome back to my channel. As you all know, this week we don't have a class because we have a Deepavali holiday this week, and some of you guys are going back home, returning back home, and then some of you guys are celebrating the holidays. So I decided to record the videos for you to refer to. So if you remember last time, we have covered class policy. So today I don't want to waste anyone's time, and then I'm just gonna jump right ahead to the main content of the class. This week, we're going to talk about, just a basic idea what is process design is all about, what's to consider, and then some design consideration and some history and different types of companies, as well as different and basic ideas about project management system in chemical and petrochemical or oil and gas industry. Yes, discuss about what's the design and integration, but yeah, we haven't really go that far yet. But I think it's a good idea for us to kind of like revisit back and then get the idea what is process design is all about first before we go into all of the technical details. Maybe in the later lectures. So yeah, let's begin. Just to recap, as we all know, we live on Earth, Earth, we have a sun, we live in a Milky Way galaxy, right? We are bound by several natural laws, and these are very important laws that you should remember because some of these laws, in fact, all of these laws are related to whatever you will be learning in this class. Also, this will be also related to whatever you'll be learning in the future and related to whatever you have learned before. For example, here, right, we have a zeroth law. By definition, it's related to temperature. It's related to temperature variables where, if you have a two system that are in equilibrium with a third system, and they are in thermal equilibrium with each other, means that the system are also the first two systems are also in thermal equilibrium. What does it mean here is it's quite simple. Let's say I'm the object A, and then I have a thermometer here, right? And then I put the thermometer to in my mouth, and then let it and you just wait for like a couple of minutes, maybe 1 hour, whatever, right? Until both of us, this object B and then me, object A, are in thermal equilibrium, right? That's one. And then let's say this object, this thermometer, right, uh, is then sent is then are in contact with the object C, right? These are object B, object C, and they are in thermal equilibrium with each other. So I can simply say that using a zeroth law, so me and the third object is in equilibrium with each other. That's what it meant. All right, first law, you have a zeroth law, you have a first law, it's conservation of energy, conservation of it's conservation of energy, it's kind of conservation of mass. So energy can neither be destroyed nor created. So it can only change form. For examples, bullet. For example, so what's a good example? So maybe a bullet coming traveling like 400 miles per hour, right? I don't know what's a normal. There's a normal. Let's say a bullet like two times speed of sound, around what around 700 miles per hour or 700 kilometers per hour, and then it being stopped. So it has a lot of kinetic energies, and it's being stopped by some a rigid wall, right? So the kinetic energy is transformed to a different kind of energy, stuff like that. And then the spring, right? Any energy stored in the spring, and then when you release, the energy will be transformed to something. Will be transformed to something else. And then you have a second law of thermodynamics. Just basically it talks about irreversibility of the process. Entropy of an isolated system always increases. But I think another, but in the context of this class, it's very important for you to remember that because we deal with the heat exchange network later on, right? It's very important for you to remember that heat cannot be transferred from high temperature to a no low temperature to a high temperature, and unless you add work. That's what refrigeration is. But again, when you want to choose your hot utility, cold utility, hot stream, and a cold stream, just try to remember that you cannot just simply transfer like a heat from water at 0 degree at 10 degrees Celsius to a, say for example, to a CO2 gas at 400 degrees Celsius or 300 degrees Celsius. So it doesn't work that way. And the third law of thermodynamics basically is the entropy of a system approaches is constant as the temperature approaches absolute zero is basically minus 270 minus 270 degrees Celsius. Why? Because at that temperatures, the materials has no more vibration. It behaves like a perfect crystal, so doesn't have any. They have no more vibration, so the entropy stays constant. Right, I'm not going to go to detail, but again, because we deal with the process design, we need to know where the process design lies in the whole, I would say, spectrum. So that's the spectrum, more like the whole flow of project management system. When you do, when we have, when this petrochemical oil and gas company, this big company, right? They get when they want to initiate a project, first thing first, they need to do a feasibility study and a conceptual design. So, but what does it mean here is just they just want it is what it literally means conceptual design. You have an idea, you have a concept, you want to try out whether you see this gonna be okay to proceed or not. And then sometimes for conceptual design, you can also compare like a one design, one concept with another concept, and then maybe compare whether it works or not. Feasibility study is just to see whether is it worth going into or not in general term, and then based on that you have an idea, you do some just a bit of just a bit it's you have a concept. It's like you design a concept of a process, and then just try to figure out whether this is worthy again for further exploration, right? And then for this one, the I think for conceptual design most of it are just simply around 20 to 30% of the cost estimate, and then the most likely the most likely deliverables is just a basic a drawing for you to communicate your concept, and then maybe helps to refine further. And then you go to 3 feet. Some company have 3 feet, some company don't. And then you go to feet, front and engineering design, or called basic design, where the cost can be further refined to 10% plus minus of your capex. And then you have and then among the key deliverables are your, calculation from your process simulation as per HiSys Pro 2, DWC, whatever you have, or maybe for a big company, you probably have they probably have their own what is called their own internal software to do calculation. You have PNID, you have equipment list, you have a line list, and stuff like that. It's basically you have a feed package that are being used for contract bidding. So when you have all that, then you go to the FID. Then the FID will take place where the board or the investor or whoever in charge is gonna do a final investment decision. And then let's say it's a go project, right? Then you go to a detailed design where it's basically you have further is a proceed to how should I say it? At this point, you have a more detailed, I'll say, more detailed information, and it's ready to be what's the word? I completely forgot, but later I'll check. But anyway, so for feasibility study until a detailed design, where these are all studies, and then it's gonna go to physical kind of like a activities where you have document, fabrication, construction, installation, pre-commissioning, and then handover. I completely forgot what's the term um for the detailed design, but later I'll check. But anyway, that's the whole idea of your project management system. This is just a more insight, like which local or international company have the capabilities, or in the whole process of project management system, where you have a this one is a you have a concept, and then you have a feasibility, and then you do fit detailed design, and then below here you have all of these companies like Dow Energy, Run MMC, Tua, Checkup, Masip. These are companies who are able to do from concept to detailed design. And then if you go to construction, you have all of these company who have, who can do all of it. But again, this class is not about, it's not focusing on oil and gas too much, but it's good to know which company uh, 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 which company uh, do this which company excel in this project management system. I don't know what. Yeah, I think that's what I'm trying to say. It's also good for you to know which company is a consulting company, operator company, and then licensor company, which I covered last time. I'm not going to go into detail, but you can see this, and then you can just simply Google, and then you see which company. Maybe this company are a company that you like to work for. I don't know, maybe some of you guys are like to be a license to in a licensor. Basically they develop technologies, they license the technologies to to the other parties. But anyway, this class is not about type of companies, but it's good to. All right. Yeah. This one, right? I found a post by this Mr. Afzal Sui. Actually, he was my students like 10 years ago. I think I used to teach him an AutoCAD class, if I'm not mistaken. But 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 I think his post is kind of like capture my attention because it's kind of related to this class. So the idea here is, when it comes to carbon capture, right, reducing CO2 emission and stuff like that, which is the main, which is something that people often talk about these days. And then you often talk and then just some of the project, and then you remember, and then you have been introduced to like a big project, for example carbon capture project, right, that try to minimize this CO2 emission. But and then, and in most cases, this project is a big project. For example, the Petronas Kasawari project, carbon capture, where they're gonna inject the CO2 into in I think in a seabed of Sarawak offshore, if I'm not mistaken. I could be wrong though, but it's a big project, right? But it's one of the, I'll say, initiative to reduce CO2 emission, to mitigate uh, to store the CO2, right? But another spectrum, and then this big project often got highlighted, which is true. But another spectrum, should I say spectrum? Another extreme is where you don't really have to go. It's not really being highlighted that much, because it could be as simple as a small project to improve energy efficiency. Now, improving energy efficiency indirectly reduce CO2 emission, because you probably will use, say for example, you use less, for example, less fossil fuel, right? Because your productivity, or your productivity is higher, is better productivity, right? Then it's also indirectly need to reduce CO2 emission. So in this class, right, we're not really talking about the the big projects. How should I say this? We are talking about increasing energy efficiency or reducing energy usage. So, which is the main goal for this class. And this also leads to a reduced CO2 emission. Now, as I said, I think there are two types. The number one is, yeah, according to him, energy efficiency initiative, which can be a small project, medium-sized project, or big project. And then another one is carbon, the CCUS project, which oftentimes you will see in the news because it's a big project. And I still remember, I think 2 years ago, I read a papers, no, I read a news by this company producing a poly, uh, what is it called? Uh, a company, it's basically a new project where a new plant, chemical plant, where they are producing IPA, isopropyl alcohol, right? Where, but in this case, they use they fully optimize their energy usage using heat recovery process, heat exchanger network, and because of that, they use less utility, and consequently, they report that this new plant able to reduce up to 50% of CO2 emission. Just something for you to consider. But anyway, now, um, what is process design? Now, uh, before that, you have to remember, we're dealing with, we are living in this world where, and we have a lot of industries, chemical industry, petrochemical industries, pharmaceutical industries, this different kind of industry, they are producing, different kind of chemicals, like commodity chemicals, where or called bulk chemicals, where these chemicals are often sold cheap, and then they are produced in large quantities because of its huge demand. For example, you have a sulfuric acid, hydrochloric acid, ammonia, oxygen, ethylene, propylene. These kind of like chemicals are being used a lot because they often act as a, either they are being used by itself, or they are a they will be used to produce something else. For example, ethylene, I think is the highest, third largest chemical commodities being produced, because why they are being used to produce polyethylene polymer. And then you also have fine chemicals and a specialty or effect chemicals. So you have a different type of chemical, but oftentimes these chemicals are not being, you don't discover them just like that. They need to be produced. In most cases, most of these chemicals need to be produced, meaning that they will undergo a certain transformation process from a raw material to this particular product, either commodity, fine chemicals, or specialty. Right? Now, so yeah, there's going to be a transformation of raw material into desired product. Oftentimes, it does not involve only one step. There are a lot of issues. I'm not saying issue. There's a lot of steps are happening because why? It's good that the material can be produced in just one step, but oftentimes that's not really the case. So so what happened here is, because there's a lot of things happening going on. So the overall transformation from raw material to product need to be broken down into several pieces. For example, here um, uh, you have probably have a process that need to convert A to B, and then another process to remove B from C, stuff like that. Because why? As I said, it's not as simple as transformation from A into B just by single step. And it often involves a lot of steps because it involves a reaction, separation processes, mixing, heating, cooling, phase changes, and stuff like that. Yeah, to give you an idea here, these are a more modern version of a ammonia production process. I took it from AICHE a blog website. It is a new technology developed by three licensor company, which is KBR, Topsoe Haldo, and then Tyson Food. So you can just Google the company. But the idea here is they want to produce ammonia. So this is your commodity chemicals. But where do you, how do they produce ammonia? Obviously they need raw material. In this case, they have air and then natural gas. So here, air is compressed to a high pressure, and then natural gas is also compressed to a high pressure, and then they undergo a reforming process, secondary reforming process to produce hydrogen, I would say, as a methane reforming, and then because natural gas consists mostly of methane, right? And then you have HTS is high temperature shift. It's basically convert what carbon monoxide into carbon dioxide plus hydrogen, basically plus hydrogen, and then you have and then you have a heat recovery here to capture to basically to extract heat, and then use it somewhere else, and then temperature become lower, it become LTS here, low temperature shift. It's still the same thing, but different temperature, heat recoveries, and then there's going to be exchange of heat to produce steam, blah blah blah. And then here you have a process to remove CO2, absorber, a stripping column, and a methanator here, if I'm mistaken, is a process where you have carbon monoxide and then carbon monoxide and then carbon dioxide. We will undergo a process to convert back to methane. And we have a dryer here just to remove moisture, condenser, and then here you have a synthesis gas compressor, basically a gas consisting of, I would say, raw materials such as hydrogen and nitrogen, and then it goes to a horizontal converted to produce ammonia, and then need to be cooled down to produce ammonia. The rest will be recycled back. So as you can see here, it's a long way of saying to produce ammonia from natural gas and excess air, or from to produce ammonia from this raw material is not, it's not as straightforward as it seems, because it involves a lot of processes. Because why? The process either produce byproducts. They are some chemicals are inert, some components are inert, some components need to be removed. So for example, you have a sulfur, some components also need to be recycled back, because you want to minimize the effluent, or I would say unwanted material discharge. You also want to remove CO2, because maybe there's going to be they're gonna poison the catalyst, something like that. You also have what else? A heat recovery, basically to extract heat and then use it somewhere else for that requires some heating or cooling purposes and stuff. You also have a dryer, maybe something you don't really like a moisture, the process does not really have high tolerance towards moisture, so that's why they remove. And of course, it's the whole process here requires high what is it called, high pressure, and or high temperature to get desired conversion. So you need to have a compression system. So as I said, it's a long way of saying that to convert to convert raw materials into ammonia requires a lot of uh, it's a complex transformation that need to be broken down into a smaller transformation. All right, phases of process design. So I think this kind of like this slides, right? They captures the evolution of a lab scale process, lab discovery, until scaling up the whole process from lab scale into a commercial scale. So as you can see here, oftentimes, I'm doing research also. Oftentimes, not many research goes to a commercial scales, because a lot of reason, but fine. So you need a quick way to screen alternative, right? So how to and then because in research is people's ideas need to be protected. That's why one way for you to get incentive, I guess, is it, or to maintain a competitive edges from the other people, right? Is just to file a patent. To file a patent is basically to protect your ideas, and then we give you an edge. Uh, give you a competitive edge for a new product that you have developed in the lab, for example. So again, let's say you have discovered a have let's say you have formulated a new product, right? So you think that it may be able to be commercialized, right? It probably have success. It has success. It may have high chances to be successful, and then you file a patent, and then just to protect it, and then because your idea you want to protect it, right? And then let's say you want to scale it up, so before process design can be started, the design problem must be formulated. Formulation of the design problem requires a product specification. So what does it say here is, let's say you have created the product. In order to produce that product, right, you need to know what's the product, I'll say purity, for example, composition and stuff like that. And then based on, let's say for example, based on those product specification, then you design several design cases, meaning that okay, maybe I can produce this product A using a design case A or B or C. So you have produced maybe three or four design. So and then you're going to examine different kind of design in order to produce the material. So in terms of like feasibility, at this point they have a very not much detail involved, but just want to see among the three or four design which one is worth progressing. And of course, when you are at this stage of a design, right, you have a lot of uncertainty. For examples, that's where you have to. So when you have this kind of like uncertain uncertainties, right, when carrying out a design, specification is often increased, and plan of over design is over design or contingency is added in order to cater for these uncertainties. But you need to remember when you have too little contingency, right? Then the plan might not work. For example, I don't maybe some situation where um, you don't really have a backup hydrogen gas, right? Or maybe you don't have any process to separate hydrogen, so the plant does not work. But during your design phase, you probably overlook this whole thing. But if it's too much contingency, you think too much. You think that okay, I need to have this, I need to have that, because you want to make sure that all of the possible, I'll say, route or possible cause of failure it will be addressed. So you have too much, you will add a lot of I'll say specification to your whole process, and then your process become too expensive. So they need to have a balance between contingency and then basically you need to make sure that you don't over design your whole process. But this one, as you can see on your left here, it is a step in the design of a chemical process. So it's the same thing I mentioned in project management system, it's good to refer back. So it begins with the conception and definition. You just try to frame what's the process, and then you deal with the flow sheet development. It's to create a block flow diagram, possible diagram, and then design equipment, and then you do economic analysis. Just want to see whether it's gonna give high ROI, or does it have what's the capex, what's the operating cost of it, and then you do optimization and then you report. So these are just a basic design, and then you have a detailed design where after FID, this is what you will do. Let's see. For this one, it's good for you to remember what's the difference between process synthesis and process analysis, or process synthesis or process design, if you will. Now, for process synthesis, you have your input, you also know your output, but you don't know what's the structure, like how can we transform this raw material A into product B, for example. You don't have enough. So you need to design a process and specify what's the parameter and then how it's connected between each process unit in order to produce an output. So in this case, you probably need to have, say, for example, two reactors, and then you need to specify temperature, pressure, and stuff like that. So, and then you need to design. So these are called processes. You design the process in order to convert a known process input in order to produce an output, the desired output. So in this case, process structure and the parameter is unknown. So it's up to you, process design or process design engineer, I would say, to design a workable process in order to convert this into this. Now, process analysis, on the other hand, you have the same thing, a known process input, and you also know output. You also know the whole, I'll say, the whole flow sheet in a sense. Process structure and parameters given. So you might be wondering, okay, if everything is known, then what's the point? What's the point of me doing analysis of this, right? Or maybe but you have to remember that just because it's already working, right, does not mean that it probably cannot be improved further. So you need to maybe analyze this whole process. Maybe you figure out, okay, maybe you figure out that uh, if I do add another heat exchanger here, right? it might be I might be able to save more costs. For example, I give you a good examples. Um, um, so a company such as Formosa Plastic, right? This company they produce plastic, polyethylene, propylene using their own process, right? So it is a known process. It is already a known process, and then the plant is already there. But 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 what they found is that no, not what they found is that one of the issues when dealing with production of propylene is the buildup of propane or buildup of ethane because this component, right, they have a single bond, so it is not really cannot react to form in order to do polymerization. So what they need is a ethylene and or propylene. But you 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 uh, you your raw material is polymer grade ethylene or polymer grade propylene, right? So this one, when you have a polymer grade, it's around 99.5% ethylene and 0.5% ethane or 0.5% propane. Goes into the reactors, right? And then they have, they know all of the process, right? But it's that over time there's going to be a build up of propane. So what they do is they flare the unreacted they flare the unreacted propane and unreacted ethane. So in this case, what if I were to analyze this and I figure, okay, if I do if I add another unit, right, a separation processes to separate using a membrane, for example. In fact, these are a true a case where they use MTR, membrane technology research in California. So they use the membrane module in order to separate unreacted ethane and unreacted propane or from ethylene or propene or propylene. So instead of flaring them, so they use a membrane. By analyzing, by doing cross analysis, they found out okay, they might be this might work, and then this might save us a couple million dollars, right? So that's what they do. So it helps for by doing cross analysis, it helps you to maybe further improve the existing process. So let's see. Yeah, in here, you do process synthesis, process analysis. You can use process simulation software in order to do all of this. Now, when it comes to process design, there are a lot of things to consider, but of course, it requires more thought, or it requires a lot of consideration. For example, here you need to make sure that when you do a process design, you need to make sure it requires efficient use of raw material. I'm not gonna use a process where I only have 20% conversion, right? And then the rest are being thrown out. So maybe I do a recycle, or maybe I change the catalyst. I add a catalyst. Maybe I do dilution. I increase the pressure. I increase the temperature. Something in order for me to make use of the raw to make sure that maybe uh, to make sure that all of my raw materials is successfully converted to what is called to the product. But it need to be done in economic and practicable way. Okay, why is this? It's because you cannot just simply achieve 100% conversion. For example, in ammonia production, right? I mean, because it's an equilibrium-based process, right? You can just simply raise the pressure up to 800 bar. But was it worth it? Probably not, because your your wall's going to be thick or something like that. And it can also increase the temperature, but then you probably need to figure out a different material for your reactor, something like that. So, but either way, you need to make sure you use raw materials as much as possible, as much as practicable, right? Now you need to make sure it's to prevent production of waste that are environmentally harmful. So you need to make sure that you don't remove H2S, for example. All of these need to be all of the pollutant need to be You need to make sure that all of the pollutants are treated before it's being discharged to the atmosphere or wastewater. Use little as energy as possible. Yeah, as I said, when it comes to cooling, heating, increasing pressure, these are all involved utility water, cooling water, refrigerant, what else? Steam, medium, high, low pressure steams, electricity. So you need to make sure that you use little energy as possible. Okay, if let's say process A requires you to this pressure to say 1 megapascal, right? Another one maybe use less. Maybe I should go with less. I don't know, something like that. And you need to make sure that we even build up of CO2 in the atmosphere from burning fossil fuels. Maybe you transform from rather than using fossil fuel, you use renewable, something like that. Or maybe you convert CO2 to something else. Preserve of fossil fuels because why it isn't not renewable, I'll say, resources, right? Water must also be conserved in sustainable quantities because why? In most of the process, you need water to do something, and then water is a finite. Water is not a lot to begin with, and then so you need to make sure that you probably can find a way to have a wastewater treatment or water treatment so that you can, instead of being discharged, you can reuse it again, something like that. Aqueous and atmospheric emissions, solid waste and landfill must be avoided, and try to minimize everything. Must also meet the required health and safety criteria. Okay, startup, emergency shutdown, and ease of control. Of course, you don't want the best process is basically the simplest process, but have the have the have the but it takes out all the important also consideration. Flexibility, ability to operate under different condition. I don't want my plant to just simply maybe at night, okay, doesn't work, something like that. But I need to make sure that it runs 24/7. Availability, operating hours, and stuff like that. These are good examples when it comes to prevent CO2 buildup in CO2 atmosphere. These are, I think I took it from ExxonMobil website. Is they set a target of 2030 CO2 emission reduction plan by ExxonMobil. So they try to so they want to try to reduction do to the 20 to 30% reduction in corporate GHG intensity, reduction in corporate flaring intensity. So they will, based on this, they will try to figure out a way to design their process or maybe improve their process so that it become better and reduce CO2 emission. All right, so these are still under process design. I know you probably have learned this, but it's good to refresh back. Now, the heart of any process is a reactor because you want to transform the raw material into a product, right? So the issue with reactor here is if it's producing from A to B, right, directly, and then no byproduct uh, um no byproduct full conversion, then it's nice. But in most cases, the reactor, yes, it transforms feed into product. You have a reactor here, feed to product, but not all feed reacts because why? You can in some cases maybe you have a full conversion, in some cases you don't, and then in most cases it also will form a byproduct which requires you to do separation. Now when there's not all feed reacts, right, you probably need to recycle or else you have a low heat or low conversion, right, you need to do something. And then because it forms because it's not fully converted, you have a feed, you also have a product, you also have a byproduct that requires you to separate them. So that's why the second thing must be a separation processes. So in here, these examples, you have uh, a housing installation system here probably to cover the unreacted feed, go back for the cycle, and then you have a product and byproduct, undergo a second separation processes produce a to separate product from byproduct. Or also, your separation processes, your reactor here does not oftentimes does not I would say it is operates under elevated pressure and temperature, so you need something to cool it down or heat it up or to increase pressure, right? Compressor or pump, something like that. And then because you have a separation process, right? You need to there's going to be a phase changes, so you need to cool down or increase the temperature. So you need a utility. Heat integration carried out to exchange heat. So this one often done last. If you ask me, process utility system will both need water. So you need water now. When you need water, you want to make sure that you use the water efficiently. You don't want to and let's say the water is initially was okay, good quality, uh, acceptable for water discharge, but then after you use, then it become it does not really meet the requirements. Like now you have to deal with water with treating the water. So water need to be processed before discharge. So you need to have maybe to treat the water, you need to have a water treatment system. Water and effluent must be considered at site level as well as the process level. This one is designing chemical processes. You can read this one. You can read this one. I'm not going to go into this, uh, but in table 15, right? The idea is like this. Now, if you want to minimize something or you want to reduce something, right? Reduce a problem, and what is the strategy? Let's say the problem here is the reaction, right? The reactor. Your reactor. How can you minimize something? Let's say the reactor produce more byproduct, right? But you want to minimize your byproduct. Maybe you change the chemistry. Maybe instead of like a one reactor, you use a different two reactor. The first one is to what is it called the first one is to deal with the first reaction, and the second one is the second. Or maybe you change the kinetics, change the you add the catalyst for better selectivity, right? Something like that. So that's the idea. But of course, when you add something new, you have to deal with the new things. Let's see. Yeah, you can read all of this, but I'm not going to go into details. But these are the consideration when it comes to minimizing waste or reduction of the problem. All right. So please read the Douglas hierarchy of decisions. So again, when you want to design a process, it's good for you to know which one is better. Is it a batch or continuous process? But in most cases, it's a continuous process, unless you're dealing with the specialty chemicals or fine chemicals, where in most cases they are producing batch. You also need to know input output structure of the function. So you have input output, what is the in between. The cycle structures, so you need to make sure because you want to have maximum yield, you want to reduce raw material usage, you want to maximize raw material usage, you need to do a cycle. So after that you have a separation, you have to deal with the vapor separation, liquid separation system, or maybe liquid separation system, and finally you do energy integration. Now, where this class really located, really where this class is, where is this class located in the whole, I would say, onion of process design? Now, as you all know, when you want to do a transformation of raw material into a product, reactor is the heart. If you don't have a reactor, then you can convert. As simple as that. This become the core of the onion, right? Now, after that, you have so here, for example, you have a reactor, you have a monomer, right? After that, you have a feed, and then goes to the reactor, and then the reactor does not always produce, does not will produce byproduct definitely, and also does not fully convert. Sometimes it has a certain percentage of conversion. So you also have to deal unreacted. You have to deal with the product. You also have to deal with the byproduct. You also have to deal with the inner, for example, right? So reactor first. Then because of that, you have to design a separation and recycle system. So they become the second layer of the onion. And then because of that, after you have complete all of that, then you can recover heat because heat recovery. Because why? Let's say you don't do any recovery. All of your I would say operating cost comes from the utilization of steam that are produced from the boiler, right? So let's say the product, let's say for example, it uses like a 1 ton per hour of medium pressure steam. So if you design a recovery system, then it maybe for example it was reduced to say 50% usage. Then you can design your cooling utilities of the after you have done the what is it called after you have done your energy recovery. And then after that, because you also deal with water, right? then you have to deal with the water next. Now, the thing that we're gonna the important concept that you will learn today is under pinch analysis. Pinch analysis is either uh, uh, what is called energy pinch analysis of energy or water. So these are the whole, I would say, onion of the process design. So as you can see, these are just another examples where you have a raw material put to the reactors and then it produce, these are monomer plus water plus a catalyst, right? So you have three things, catalyst, water, monomer. So the reactor, it goes, it become a polymer, a still unreacted monomer, still a water, and then a catalyst. Now at this point, they become a solid, polymer becomes solid, so you have to wash with water. Basically, the solid, it's kind of like you really wash the polymer solid to make sure that the unreacted monomer, water and catalyst goes back. And it happened in the filter, so you have a, and then you do, and then you recover unreacted monomer, and then you cycle back, go there, and then you have water here, right? Water here, and then need to be, it is become effluent, then this need to be treated also. Now you have a solid, basically after you wash, it's like a, you have a kind of a wet polymer beads or wet polymer solid, right? Then it goes a dryer. That now, oftentimes in the dryer they will run with a hot air or hot nitrogen, if I'm not mistaken, so that it become a dry polymer. And of course, this is not being shown. Now you have to deal with the hot air as well. Maybe you want to remove the moisture after drying process. So yeah, when you want to design a chemical process, there are a lot of things to consider. Fortunately, we have a lot of computer-aided tools to help us out. Again, AutoCAD, PNID, AutoCAD PNID, AutoCAD Plant 3D. You have process simulators, a lot of things. So, in order for you to create an environmentally conscious process flowsheet analysis, you have to consider a lot of things. For example, here, process integration, environmental impact. Properties here is also important for you to make sure that you don't, the process actually, you really mimic the actual process. If you use a wrong thermodynamics, you probably mimic it does not really describe the correct behavior of the chemical mixtures under a certain process condition. You have a process models, optimization, multi-objective, mixed integer or non-linear, for you to figure out, okay, which configuration of heat exchangers can I use, and what are the percentage of, let's say, for example, of energy or stream or I'll say a hot stream or cold stream that need to be split in order for me to really optimize the energy recovery, something like that. Possibly, yeah, okay. I think it's probably the second last slide, but the idea here is you need to know process integration is not new, but it's very important. So these are a short history, but back in 1970s, it started being introduced. The concept of heat integration start to be introduced because why? If you see here, there's an oil crisis where all of the Western companies they face a shortage of, I would say, oil, crude oil, because of why? Because of Iranian revolution as well as the Yom Kippur War, if I'm not mistaken. As you can see, between 1970 to 1985, the oil cost per barrel, right, start to skyrocket. These are the real values. These are nominal values. But as you can see, it is being introduced because why? And then they got and then the concept of heat integration, they get a good attention during the oil crisis. So it is first established for optimal synthesis of heat exchanger network. Now, and heat integration is also is intended for optimal synthesis of heat exchanger network, followed by efficient design of various energy-intensive processes such as distribution utility system, etc. Right? It's already reached the mature stage, slowly built since like 60, 70, 80 years ago. And there are a lot of books, references, review articles available. We can read. I don't want to go to details. And but the second one here is about, the first one is about heat, right? The second one here is getting more popular, mass integration. Basically, instead of energy integration, you do mass integration. You want to maximize your loyalty. So it's the same thing. It's the same thing. It's more or less the same concept as heat integration. But in this case, we use a mass transfer. So driving force, we want to minimize waste. It's part of the initiative to minimize waste. So I don't really want to. I think this is the last slide, but one thing for me to highlight here is, what's really happening these days, right? So in addition to mass transfer as well as in addition to mass integration and heat integration, the first one is property integration. You can just take a look. Water minimization, refinery hydrogen network, and then an energy sector planning. They do this, I'll say, integration processes in order to minimize energy sector supply chain process scheduling. They want to minimize how can we make our process how can we schedule our process more optimal. Financial analysis also been done. So these are a few papers that I take. Maybe if you want to read, you can read. These are just another examples where people do optimization, mixed linear. I'm not really an expert on this, but they use a mixed linear approach, whatever approach they do in order to use common resources as well as internal resources in order, and then waste, and then dedicated resource demand and various zone, and try to see what's the most optimum, I would say, objective. What's the most optimum solution here? This paper is this one, I think, but this one, no, this paper is optimizing segregated resource conservation network with cross-sectional zonal transfer for multiple resource projects. So basically, you have multiple resources. Basically, this paper, they use a cross-zonal transfer. You have a multiple resources, you have a multiple quality of resources, and then you want to see how can we optimize the resource. The second paper here is, don't really remember, clean technology and environmental policy, systematic rate profit procedure for resource conservation network based on pitch analysis technique. So it's kind of they have existing. I would say I haven't read this one for a while, but I think systematic retrofit here means they want to improve. They have existing plans, so they want to retrofit. Just want to add a unit in order for you, in order for uh to conserve to create a network to conserve resources based on pinch analysis technique, which we will learn later on. Yeah, I think that's pretty much it. So I'll try to upload right after this. So password is already shown. So try to search. Um, yeah, make sure to record your attendance on Club, and I'll see you next week. All right, bye bye, and have a very nice day.